Morgan, this one's for you. Hope your trip is going well. You're going to see some colleges, so I hope that spurs you to even do better and better while you're here. So you can do that. All right, we're going to do two sides here. And this is showing up.
Yes.
All right, this is derivative land, and now we're in your comp books. So this gets written down, and this is integral land. So once I give you these, we'll be able to do a couple problems. I'll do about 3, and then you'll be set to go on integration. We started this a little bit yesterday, so just pick up now with this little chart. All right. Let's start with the most important one. It's the power rule for derivatives, which will be the power rule in reverse for integrals. All right, so the power rule for derivatives. So you'll recall that we did the derivative. Remember that symbol I taught you about earlier today? Morgan, we went over the homework and this symbol showed up. All this means is the derivative of this expression with respect to x. So that's what d over dx means. And we learned that the n runs down in front and then reduces by 1. So we've been using that a lot already this year. So let's talk about that over here in integral land. Take the integral of x to the n. And remember, every integral is followed by a d something to tell the reader what variable we're working in. So we're normally working in x, doesn't have to be, it can be dt or dr or whatever, but a lot of times it's going to be dx. So the integral is x to the n plus 1 over n plus 1 plus c. And we talked about that already on Wednesday, and we talked about why the c was there. Please note, n cannot equal 1. So, all right. Next one. The derivative of the sine x with respect to x is cosine. So integration undoes what the derivative did. So what would be the integral of the cosine of x? dx. It's going to undo what we did over here, so will it not bring you back to the sine? So you have to remember plus c, of course, always crown it. All right. So we're going to go down the line, going back and forth, and then when we have all ours listed, I might have to finish over there. I'm already seeing they're not going to fit all my trig functions. Try this one. See if you can figure out what's going to go in both lands. Because we know the derivative of cosine. We've already played around with that this year. So what are you writing, Erin? What's the derivative of cosine?
Is it just sine?
It isn't.
Oh wait, the derivative of cosine, negative sine.
Yeah, right. So now you could say what's the derivative of minus sine, but let's do positive sine. That doesn't mean we can drop the negative relationship between these two, so it's just going to show up on the other side. So the derivative of sine is negative the cosine. Do you see how that's directly opposite what it was over here? The derivative of sine was cosine, the derivative of cosine was negative sine, but in integral land, the integral of cosine is positive sine. See over here, the derivative was negative. In integral land, it's positive. They work differently. And the integral of sine is negative. So you got to kind of recall that when we switch to integrals. So it's not always easy. All right, the next one, the derivative of tangent. Was secant squared. So over here in integral land, we can only do secant squared. It works the opposite. We can take, if secant squared ends up in our problem, we can integrate it because of this relationship in derivative land. And similarly, The derivative of cotangent is negative cosecant squared x. So, I'll make sure you caught up with me. I don't want to zoom ahead. The integral of derivative is negative cosecant, so we can take the integral of that, but usually I keep the negative sign on the other side. I don't have to, as long as one is positive and the other is negative, but it's just sort of more pleasing to look at it like that. Okay.
Did you forget
Plus
to crown them?
Oh yeah, thank you. Crown them with many crowns. All right, so I've got two more. Actually, you know what? 1, 2, 3, 4. Yeah, I do have two more. So I'm not going to be able to squeeze those on. All right. What do I need? I have sine, cosine, tangent, cotangent, secant. So the derivative of secant x with respect to x is secant tan. I'll move that over as well. A second. Derivative of secant with respect to x is secant tan. So when we switch over to integral land, we can find the integral of secant tan and get secant and crown it. Last one, derivative of what's left, cosecant is negative secant tan is negative cosecant cotangent. So keeping it positive, and I forgot some dx's over here, so make sure. Kind of interesting, your assignment and the examples, most all of them come from the first line. And we had to put all this Hoostruck on here just for a couple trig ones, but we do have to need them. So, anyone see anything I forgot in terms of dx or crowning? All right. All right, let's go ahead then and switch over and I'll just do two examples. And I'll do one that's trig and one that's not. And then I'll let you try it on your own. All right. All right, the first one, example I'm going to do is the integral of 1 over x squared square root of x times the square root of x. And that's dx. All right, as I foretold you, that almost all of these are going to come from the first power rule. There's no trig function in it. So really, the way you integrate this is your success is to see how snazzy you are at algebra, changing this to look like x to the n. So how snazzy are you? Can you combine and alter all of this here so that it is x to the n? So what do you think, Gianni?
You could combine the x squared and the square root of x, so it would be
Right.
5 halves.
So on the bottom, this is like x to the 1/2, is it not? So how do you combine exponents like that?
You add them,
And what do you get?
x to the 5 halves.
Right. So now it's still not quite in the x to the n form. Here's what, keep your eye on the prize. We want it to look like that. So then, Gianni, what do I do to make it look like
You
that?
can make the exponent negative and bring it up to the top.
Right. Now that's snaz. You're very snazzy. If you can take this expression and make it look x to the n, then you're home free. So all of this becomes 1 over, becomes x to the minus 5 halves, and then I'll put in my dx properly. All right, are you caught up with me, Erin?
Mm-hmm.
All right, tell me then, follow this formula. Right here, it's gonna be the big deal one. So how do I get the integral?
X, plus, and then it'd be negative 5 halves plus 1.
Which is, so,
Negative 1 half.
negative 1, 1.
Oh no,
No, plus 2
Negative.
halves.
3 halves.
Right, negative 3 halves divided by?
Divided by negative 5 halves plus 1 again, so it would be
No,
negative.
because in the formula, notice the n plus 1, which you just calculated to be negative 3 halves,
Yeah.
is repeated underneath. So I thought you said over 5 halves. Okay, it's over 3 halves. All right, and then we don't usually leave the negative 3 halves down. We flip it and turn it into a coefficient. All right, you see how we use that formula? You remember doing that in the past? Okay, so all the ones in X in your assignment is just an exercise in seeing how snazzy you are at getting it to look like this.
It's been 11 minutes. Should I do
Yeah,
a new one?
I guess.